Hello, everyone, and welcome to the Brain Talk webinar. Brain Talk webinar is an online platform where scientists, researchers, and early-stage researchers have an opportunity to present their research work, which is related to machine learning and computational sciences. I am Ghadi Al-Hajj, and it gives me great pleasure to co-chair this webinar with Moeen Naqvi from Simula Research Laboratory and Sajjad Ahmadi from University of Oslo. This webinar will be the last webinar of the year, and we will be back again next year, just as a note. And with this, I would like to give the stage to Moeen.
Thank you so much. Today we have a very interesting presenter. After this presentation, we will have a question and answer sessions, and audiences can post their questions on YouTube live stream. The presentation is given by Aizaz Sharif, and Aizaz is a PhD researcher at Simula Research Laboratory and with the University of Oslo under the Department of Validation Intelligence for Autonomous Software Systems. His PhD research is focused on testing and validating autonomous driving systems that are operating using artificial intelligence-based software. He is currently working under the supervision of Dusisha Marijan. Hello, Aizaz. The floor is yours. We are looking forward to your presentation.
Thank you. Thank you. I think everyone can see the screen. Yeah, so thank you, Moeen, and for the introduction. My name is Aizaz. I'm a PhD student, and today I'm presenting one of my thesis work, which is testing and improving the robustness of self-driving cars using adversarial deep reinforcement learning. So this is the overall content I will be covering, where I will give a brief introduction to autonomous systems and the challenges that lies with testing of autonomous systems. And then I will go through the research gaps and the challenges that we identified in my thesis, and then the proposed solutions for those challenges, along with some future directions. So autonomous systems are emerging technologies that are becoming vital in our daily lives. And there are a lot of different versions of autonomous systems. The most common that we see around is like autonomous cars, autonomous robots, and the type of autonomous systems we are working on or focusing on is autonomous cars. So autonomous car is a system that can automatically perform a predefined set of tasks under real world conditions. And government and regulatory bodies have defined certain level of automation levels, so that the higher you go in autonomy, the more a society can trust on such autonomous systems. And these autonomous systems are mostly working as part of AI-based systems. So AI is getting a lot of attention and is used by large tech companies, as we are seeing, whether in vision-based models or large language models. And AI is slowly transforming into cyber physical systems, as mentioned, like self-driving cars or home service robots or vacuum robots. Then what is the main challenge for such autonomous systems if they are that well? The main challenge is many of these AI-based autonomous systems work in safety critical environments, and which is why they are very difficult to be tested in the real world. And on the other hand, if we don't test them properly, they can be very, very dangerous to the society. So there is a need of efficient testing of autonomous systems because it can create a direct societal impact. And testing is required to build trust in AI-based systems around us. And in the past few years, a lot of research has been focused on finding the vulnerabilities in to expose the failures in autonomous systems. So this is just one example from the researchers from Stanford, where they proved they provided a framework where to show that autonomous systems were failed to hit the brakes when the pedestrian were crossing a crosswalk. And there are many other examples for such vulnerabilities. So how do we go for the testing? So there are two main options for safety validation. One is the real world testing, which is very expensive and risky. And then there's a second option, which is simulation-based testing, where you can simulate challenging scenarios, propose different solutions, and there is no risk to the real world. And fortunately, at least now, not only in industry, but in academia, we have solution. We can now trust simulation-based testing, especially in testing autonomous cars. With that, there are a lot of research gaps and challenges that we identified in my PhD that are still like yet to be solved. So I grouped them in two parts. The first part is mainly focused on the choice of training autonomous cars algorithm, like how do we solve that problem. So I will go through these first three challenges with the proposed solution. So the first challenge is majority of the autonomous driving research is focused on using deep reinforcement learning as the first as the main go-to option, which is a good thing because they show a lot of good results. But there is no such benchmark or there is no such comparison of like which type of algorithm we should choose, because there are many types of deep reinforcement learning algorithm, and we don't provide this kind of comparison. So especially for a vision-based urban driving scenario. So that is one main challenge. The second challenge is we still consider autonomous car problem or autonomous driving problem as a single agent problem, while it should be moved towards multi-agent problems, because when there are more driving cars, that impose a lot of challenging scenarios. And the third challenge is if we are talking about reinforcement learning, the one of the key components of designing a reinforcement learning algorithm is designing a reward function. And we still lack evidence of a detailed multi-objective reward function that can be utilized within multi-agent deep reinforcement learning algorithms. So there is an ongoing research on designing a better reward function, which is highly required for better autonomous driving. But so far, they are still focused on single agent driving scenarios. So with all the three challenges that I have mentioned, we feel like there is a need of a benchmarking framework for the comparison of deep reinforcement learning in a vision-based autonomous driving environment. And it will open up the possibilities for training better autonomous cars in the future. So we propose an open and reusable end-to-end benchmarking framework for the solution, where it enables to bring competitive and independent multi-agent driving policies in both single agent and multi-agent scenarios. And we also provide a comprehensive multi-objective reward function designed for the evaluation of simulation-based driving policies. And within this framework, we also validate the framework by performing a comprehensive evaluation of the robustness of such algorithms in both single agent and multi-agent scenarios. So this is the architecture where each autonomous car is working independently, and by taking observations as input, it processes it through a reinforcement learning algorithm. And we have selected total 6 reinforcement learning algorithms. 4 of them work in discrete action space, while the 2 work in continuous action space for the comparison. And based on their action space, they select an action of whether like go for steering, throttle, or brakes. And the selected action is provided to the environment, and then we select the next action. And there is this whole loop of reinforcement learning algorithm. As for reward function, as we mentioned in the contributions, one of the contributions was we provide a comprehensive multi-objective reward function, which can be formulated as the following. So the reward function can be divided into 3 or 4 parts. The first line talks about the safety. We provide the safety in autonomous driving by giving a negative reward to any sort of vehicle, road object, or pedestrian collision. And similarly, we give a positive reward to efficiency by like covering distance and speed. And similarly, a negative reward is given to any kind of off-road steering error, so that it encourages for lane keeping. So for our results, we have 2 research questions. So the first one is talks about which deep reinforcement learning based autonomous car work in both multi-agent and single agent scenarios. And the second one looks from different angle, which is the success rate. of the same deep reinforcement learning based autonomous cars. We go through these 5 different driving environments for training and validation of the deep reinforcement learning algorithms. So you can see that we have environment called straight road, 3-way intersection, 4-way intersection, roundabout, and merge, and they all correspond to the real world driving scenarios. And this is the similar thing where first we look into a multi-agent scenario where a car can come across a pedestrian and another car, while the same trained models will be used in a single agent scenario to see their robustness in a situation where there is no car around. And in order to build this end-to-end benchmarking framework, we used certain tools and libraries. So one of them is Carla, which is a famous urban driving simulation framework, RLLib, which is a very fine-tuned and scalable reinforcement learning library. The third one is a open source framework that connects Carla, RLLib, and OpenAI GM toolkit, and we have modified and tuned it. And one of my main contributions is to add functionalities in this in order to propose this benchmarking framework. And the last is TensorFlow, which is one of the leading frameworks to create deep learning based algorithms. So if we just look at the first research question, there's a lot going on in this table, but just to summarize, we are looking in scenario 1 as multi-agent testing and scenario 2 as single agent testing. And the values closer to 0 means while testing, there were no errors found, but closer to 1 means there were high chances of error. And as a brief summary, what we can say is A3C in discrete action space and TD3 in continuous action space performed much better in comparison. And we can see the same kind of results in the coming slides. This is evaluation with respect to average speed doing the simulation testing. And one thing to notice is A3C and TD3 might not be having a lot of speed as compared to DQN or Impala. But in the coming slides, we will see that more speed does not correspond to better performance, because with higher speed, they collided more with other cars and road objects, while A3C and TD3 performed much slow, drove with much slower speed, but they also were more safe. So they had a trade-off in their learning. So these 3 rows correspond to the first 3 driving environments, while the other 2 are the rest of the 2 driving environments, total 5 driving environments. So this is the success rate of autonomous car driving policies in achieving multiple driving objectives with respect to the reward function that we have proposed. And the first aspect is safety. And when we go through all the driving environments, we see that A3C and TD3 are much safer with lower rate of any collision with vehicles or road objects or even pedestrian. But not only they are safer, they are more efficient. So if we look for the speed, they might not be having a lot of speed during the testing phase, but they covered more distance throughout the testing phase. And same with the lane keeping, A3C and TD3 in our experiments performed lane keeping with a lower rate of any off-road steering errors. So these kind of results and comparisons can improve our research in proposing different solutions to keep using reinforcement learning algorithms for autonomous driving, because so far we didn't know which kind of algorithm should be used in the future. So we propose this paper as a benchmarking framework along with the code, and it has been recently accepted in the International Conference of Software Security and Reliability. If we go towards the second part of research gaps and in testing autonomous cars, then in the first part, we were talking about just a basic comparison, like in a normal testing scenario, without proposing any adversarial attacks, any adversarial solution. Now we will look into that aspect. So the first challenge we look is a lot of research has been proposed on scenario, test case generation, and input validation for testing autonomous cars. It's a way, these are the main fields in testing autonomous cars. But we mostly stop on the detection part, and we usually do not go on the correction part. So like if, for example, there is an adversary, any kind of adversary, which we have used to find failure states, how do we use these kind of test cases to improve the same autonomous cars, which we call victim policies in our paper? But like, how do we correct them? How we can make them more robust? That is the main challenge. The second is there are a lot of scenarios which we call like simplistic evaluation scenarios that is like commonly used in the research field. Sorry. So the first one is like the academia research is still focused on single agent problem, which is limiting a lot of issues in driving. The second is lane keeping and mixed traffic scenarios. The moment we scale towards bigger problems like mixed traffic systems, they are kept in low dimensional space. The third is we see a lot of papers proposed for testing rule-based driving systems. So a common example for rule-based driving system is like the kind of cars we see in a gaming world, which are automated, but they cannot be scaled to improve. And like testing such system is not like a very good approach, because they are not AI-based systems. And the last thing, which is offline testing, is testing based on some offline stored data rather than the simulation-based testing, where we limit ourselves to single-based testing. Although there is recent progress in this field, where now you can even include multi-agent scenarios. So these are some challenges. And the third one, which is the most important one, is as I have mentioned in the previous paper, we use reinforcement learning a lot in training autonomous agents as well as autonomous or self-driving cars, especially in academia side. But in parallel, there is an ongoing field where it has been proved that these autonomous agents, which have been learned using reinforcement learning, are very vulnerable to adversarial attacks, even in a black box manner. So, and that is actually a threat to the same kind of autonomous agents in self-driving manner. So how can we deal with this? Or is this hypothesis even true when it comes to self-driving cars? So to address all of these, we proposed a framework called MAD-ARL. And here we proposed a two-step methodology. In the first step, we will go for finding scenarios using an adversary. But in the second step, we will use the same adversary to increase the robustness. And for that, we introduce a framework where driving policies can work in a multi-agent and independent environment. And for training an adversary, we design adversarial agent as a driving agent itself. So the adversary will also be a driving car, and the driving car will work in a way that it will try to learn some movements which will be considered as adversarial to the self-driving cars, without any access to the white box access to the autonomous car model. And we experimentally demonstrate that retraining such self-driving cars using adversarial driving models can be effective defense against the adversarial attacks. So to show this in a pictorial way, this is the architecture of our MAD-ARL framework. The top row shows the first step, which is dedicated to finding failure states, while the second step is dedicated to our two-step methodology, which is how to improve the robustness by retraining. So in the first step, we have two cars for our use case, and the two cars are represented as blue, which is self-driving car, or called as victim because we are testing them. And there is an adversary car represented as red. And once we train the adversary, then we can we will show that the victims went into failure states when they faced such adversaries. But we retrained the self-driving cars by fixing the weights of adversary and retraining, after going through the retraining, they improve their robustness, because such adversarial use cases were not present in the normal simulation training of the self-driving cars. As for the reward function for adversarial agent, so you might be wondering why there are two different types of reward function for training adversary, because we are proposing two different kind of adversarial agents. The reason is one can think of like what is the better way of training an adversarial driving agent. So the first option that comes to your mind is you train an adversarial agent with the notion of having more collisions. So the moment it sees a self-driving car, it tries to collide with it, but it is not very realistic. And in the coming slides, we will show that it is also not very efficient. But there is another way which is only focused on the off-road focused adversary. So what the adversary learns is just some weird off-road steering movements, and those will be perceived as adversarial attacks even with a distance for self-driving cars. And the other one, which is off-road based adversary, will be just fine. These are just hyperparameters for the overall training of in the different time aspects. So the first one is the baseline, which is the self-driving cars and their training. Then we will go for the adversarial training, and then we will retrain the baselines using the adversarial attacks. One thing to note here is the amount of episodes used, or the amount of training steps used for adversarial training is much less than the baseline training, which shows that adversarial training will not take much time to learn different scenarios where they will fail. For evaluation metrics, we use four following metrics. So the first one is for the rate of collision with another vehicle. The second one is for the rate of collision with any other road object. The third one talks about any off-road steering error, and the fourth one is used to calculate the time it takes to have the first collision in the simulation testing. And this is an experimental setup to understand better how this whole training and testing works, because sometimes it gets confusing. So if we start from the top left, we have a baseline scenario where there are two self-driving cars and they're performing without any adversarial agent, and they're performing just fine with very less collision or off-road steering errors. And then we introduce our two different types of adversaries. And we show that if the self-driving cars are trained on similar kind of reinforcement learning algorithm, then just by training adversary against one victim is equal to like generalizing to multi-agent scenarios. So we are only training against one self-driving car. And then we in the bottom we show we go through the testing phase where both self-driving cars come across these adversaries. And after the testing phase, we also use the same scenario for retraining. And this is the performance of our adversary training, where the collision-based adversary performs slightly like it does not perform as well as the off-road based adversary. So in the results, we want to evaluate the effectiveness of adversarial driving policy for finding the failures, but we also want to know the whether we can improve the self-driving cars in the retraining phase or not. And and in this table we show our main results, and this table can be easily visualized if you go from left to right. So on the left, we have our baseline performance, where there is pure testing of this self-driving cars without any adversary. And we can see that there is hardly any collision detected with any other car. And there is minor collision with road objects and very minimal off-road steering error. In the middle four columns, we bring our adversarial training and testing. And we can see that by bringing the adversaries, they started to collide a lot, and they also had a lot of off-road staying errors. But one thing to note is between the two type of adversaries, the off-road based adversary performed much better in exposing the vulnerabilities more, even by keeping a distance. And then we use the same adversaries by introducing the retraining of the same victims, and we see that in the blue, especially that victims performed much better because now they have different type of use cases where they have the adversarial agent in front of them, and now they are performing much better because now they have this they have retrained their policies. But these are the average values among 50 episodic testing. If you go through all the different values, then this is the same kind of result, but in a box plot. And from left to right, we can see that on the left, we have a baseline performance where there is little to no error. Then in the middle, we introduced our adversaries, where the error increased to almost like higher probability, closer to 100%. And then by retraining, we went down to better performance by increasing the robustness. And this is one of the this is taken from one of the testing phase, where the top row shows the first step of our methodology, and this bottom row shows the second step of methodology. So in the first step, we are going through the testing phase, where in one scenario, the victim one failed by going off-road. And also in the second picture, we see that the blue car, which is the victim two, it directly hits the footpath. But when we retrain them, we can see that now they have increased their robustness, and their driving behavior has been is now better. One thing to note here is like the time expect is missing. So it might looks like the adversary is colliding with them, but this is just a two-dimensional representation without the representation of time. So we conclude our work by proposing this framework and this two-step methodology. And this work has been recently presented and accepted in the Asia Pacific Software Engineering Conference, which is APSEC, and the code is also available on the GitHub. So there can be a lot of future directions, but the two main future directions I'm working on currently in my PhD is to extend to autonomous cars operating in mass traffic scenarios, where not only you have more cars, but pedestrians and a whole network of traffic light as part of a multi-agent scenario. But it is challenging not only from like the coding perspective, but also from theoretical perspective. And the second, which is an active ongoing work, is to investigate how to deal with this problem of like right now you have seen that we know the autonomous cars are using reinforcement learning, but what if we remove this this information? What if they are using imitation learning? What if they are using behavior cloning? What if we just treat it as a black box manner, a black box problem, and we only consider their action behaviors and distributions to validate their performance? Is it possible? So I'm trying to investigate this problem, and that is all on my side. So thank you for listening to this presentation. If there is any question, please you can ask.
Thank you so much, Aizaz. It was such an interesting presentation. I have a couple of questions. First of all, I would like to ask about like the differences between using simulation and like in real world. There has been like a lot of discussion in academia about like the challenges you face sometimes which are not represented in simulations, which you can face in real world. So how do you think like how realistic these scenarios become if you want to put these systems, a well-trained system into like real world?
Yes, like that is actually a very good question, and that is actually the main concern in academia, especially. But especially during pandemic, a lot of progress has been made, at least on the industrial side. If you see the examples of like the well-known self-driving car companies like Tesla, so they internally have made such softwares where they can generate close to real-world scenarios to verify their model performance. And they recently presented their software in a conference as well. So now in the last 2-3 years, people are moving towards like trusting the self-driving cars. So this is one approach, but on academia side, there's people are also going towards the testing of offline testing. So you cannot no matter what you do, you cannot have a close to real world simulation environment in simulation. So but what you can do it, you can collect real world data in the form of like images and test your model. So these are the two directions which are now very much trusted in simulation testing, at least in industry.
Yeah, thank you. Another question was about the formulation of reward function. I mean, you discussed and you presented, you showed like the reward system that you have used. What were like some considerations behind like what weightage is important, and perhaps was there like some fine tuning in the process? I'm pretty much interested in knowing the process behind choosing this reward function.
Yes, yeah. So in my future work, what I'm trying to look into is also like automation of the reward function, because this is one of the limitations. You need to know you need to fine tune a lot of, like you have to go through a lot of different hyperparameters and a lot of different settings to decide what a reward function can work. And this is the same as that. Like I went through a lot of different settings for looking at which kind of reward, whether in a positive way or negative way, would work. And this is like, you can say, in a manual way. But for training the hyperparameters, like the model training, that is actually automated using algorithm called population-based training. So it's a search-based algorithm which selects the best possible hyperparameters. But for reward function, you can say it's manually done.
I see. And is it like based on heuristics, or how big is the search space here?
For this one, it's not big, but if we talk about the training, then there is a whole table in the paper where we talk about, like, because different algorithms will converge differently. Like some might converge in the earlier episodes of the training, some might converge to a better performance later. So this can be all automated using this PBD algorithm. And we used it to somehow like use different values. Like we select the 3 or 4 based, for example, learning rate or a different kind of hyperparameters to, and the algorithm will decide like this one is the best one for this.
Thank you so much.
No problem.
Are there like questions from you? Yeah,
I have a question about this slide specifically, and also I wrote this question in the chat room. Would you please describe briefly the different parameters in your reward function, for example, CVT, COT, and this is the first part of my question. And the next part of my question is when we say safety or efficiency, what we are thinking about in your model.
Yes. So in this reward function, we are using certain values in order to like produce a reward value in the training. So CV is collision with vehicle, is the short form for that. So we are using the collision with vehicle, collision with road object, and collision with pedestrian. as one of the metrics, and so they are Boolean values. So if even in one of these values are on, it means that there was some kind of collision, and we give a negative reward of -50 as a constant. And the same is for the other one, where d is the distance from the spawn position till the distance it has covered, plus f is the forward speed. The third one is off-road steering error, which is like how much the car is driving in its lane. And if they even for a single time for certain time steps the car is not driving, then the Boolean value will be 1, means there was some errors, and we give it a negative reward. As for safety and efficiency, if the car is not colliding with any of these, then we call it safety. But in efficiency, this can be more clear with this. So in efficiency, we are not only we are considering the speed, but we are also looking into the distance part, because lower speed might not correspond, like higher speed might not correspond to like covering distance, covering a lot of distance, because then we have to look at the other dimension, which is whether they were safe while having this much speed. So this is the efficiency, where we look into speed and distance at the same time.
And also, I have another question about slide 37. You have mentioned, you were talking about experimentally testing your model. Did you get a chance to test your model industrially in real world in real world, or it was just testing by the model and train and test? How was your experiment?
Yes, so far we are only using simulation testing, and any real world example was not used. Although we are trying for it, because there is a company called Comma AI, which is in competition with Tesla, and they provide their models, and that can be used in Carla-based simulation. But they are limited to single agent setting. So, which is why. Which is one of the limitations in the current academia work, is a lot of models, especially deep reinforcement learning based self-driving models, are available on the internet, but they are very difficult to use for your work or for proposing something. So far we have done the simulation testing on our own.
Regarding these self-driving cars, I would like to give a big picture of your work to our audiences. How far we are to have a smart city with self-driving car? You are, as a researcher who are working professionally in this field, do you think we are very close to make a smart city? And for example, maybe after 2, 3, 5 years, we have a smart city with self-driving cars, or still we are behind of this idea?
Based on my observation, I think we might be a little, we might not be close to a smart city. We have started using self-driving cars, as we can see in certain areas of United States, where now like self-driving cars are used as taxis, or delivering like delivering Amazon packages. But but there are certain challenges, like in the testing, just like I mostly emphasize in my thesis about the multi-agent problem. And in the last few years, a lot of researchers, and whether in industry or academia, are also starting to talk about this problem, which is why we are not able to, we have not been able to like fully utilize self-driving car problem. So because of this limitation, I don't think so. It might like it's very close to be like public, especially. And this is the main one problem. And the second problem is there's there's vast majority of scenarios that the self-driving models have not yet seen, especially the areas like in Asia, where like the self-driving car has not learned anything, where the rules might be different than what we see in like on the west side. So there is still some time for at least for self-driving cars.
Thank you. Ghadi, you have no question?
I just have a very quick question. Slide 35, where you show the hyperparameters. Do you have like a policy to decide on these numbers, or do you just follow a validation data set?
Sorry,
Like how do this? Yeah, can you hear me now?
Yes.
Oh, yeah. So how do you decide on these hyperparameters? Do you have a validation data set to decide on these, or is it like, do you have any other policy or something?
So for training and as well as validation, we are using the simulation. So we don't have any data set, but we have simulation environments where the models can actively not only like train by trial and error, but we can also validate their performance at the end with the final model. And with these kind of hyperparameters, we have a baseline first where if I can show. So like on the left, we can see that 0 corresponds to no error. So based on these kind of metrics, we finalize the hyperparameters that, okay, so these self-driving cars based on these are like performing the best with minimal off-road steering errors, but no collision with cars. So that's how we decided for the hyperparameters in this work.
Okay, so they are not like pre-defined in a way, like before you start the training, you decide on how many episodes you want to have and how many iterations, but you just do it on the fly in a way.
Yes, like you obviously give a very high value in your training as a maximum, but the like for example here like the total training episodes that the self-driving cars have used is like 610, but during the training we provided like 3,000 4,000 training episodes option, but they didn't reach there and they were optimized even before there.
Yeah, thank you.
No question.
I would like to ask one more question, and it's more like an advice for people who want to use adversarial learning in their research or in their work. How would you advise people to model their problems? Like, what can be a good sort of starting point for someone who is new in this area?
Yes, so adversarial machine learning has like a lot of different subfields right now. So adversarial machine learning started by using mainly using generative adversarial learning, which is also known as like GANs. So we produce some images which are like new and have not been seen by any model before. And during the testing of self-driving cars, a lot of researchers found out that like this can be used as adversarial testing. But now, so that's the main point where people usually start practicing adversarial machine learning. So as a starting point, I would suggest that for adversarial machine learning, go through the main foundations, like how generative adversarial networks works, what is meant by adversarial learning, and what can be called adversary and what cannot be called adversary. So there is a difference, like adversary can be like randomly adding noise in an image or input, but here I'm working on the opposite field where you don't have access to the input or the models of the self-driving cars, but you're still creating adversarial attacks, so it's black box. So I think this might be more towards the black box, but people mostly start with the white box adversarial testing.
Yeah, thank you so much. It was very helpful.
Mm-hmm.
I would like to give the platform to Ghadi now.
Ghadi, do you have anything to add or question?
No, thank you. Thank you.
Okay, just a brief chat with our audiences that this webinar is the last webinar of the year, and soon we will back to you with very interesting topics in New Year. Thanks for all supports. Thanks for watching us and sharing your comments and ideas with us. You know, our email is dscience.brain@gmail.com. Please share your ideas, your comments about our team, about our speakers, about our style of webinars. Share your brilliant ideas with us and let us to improve ourselves. Thanks, Aizaz, for attending to our conference. It was our pleasure to have you here today. And I wish the best for all of our audiences and for Brain Talk team and Aizaz, our guest for today in New Year. See you next year. Bye.
Yeah, thank you.
Thank you. Bye-bye.
Bye.